Optical OFDM for visible light communications. Due to the intensity modulation property, the transmitted signals are constrained to be real-valued and non-negative in VLC. Typically, Hermitian symmetry is imposed on the frequency domain subcarriers to generate real outputs after the IFFT, and the symbols modulated onto the subcarriers satisfy. Where niche the number of subcarriers in OFDM. Moreover, x0 and xn/2 are set to 0 for the same purpose. After the IFFT, the resultant time domain signal can be formulated as which is bipolar, and various techniques have been proposed to obtain non-negative waveforms for transmission. When n greater than or equal to 64, the distribution of Zn is approximately Gaussian with zero mean. In the following, DCO-OFDM, ACO-OFDM, PAM-DMT, U-OFDM, and hybrid optical OFDM schemes are introduced, and the diagram of these schemes is illustrated in Diagram of optical OFDM schemes for VLC. A natural way to obtain the unipolar signal is adding a DC bias to the bipolar signal while clipping the remaining negative signal at 0. We denote the DC bias as XDC, which is usually proportional to the square root of the electric power of Zn, 2. Since the expectation of Zn is 0, the optical power of the transmitted signal is proportional to the DC bias when clipping distortion is neglected. A large value of Zn leads to small clipping distortion, which is beneficial to the burr performance at the receiver. However, DC bias does not carry useful information, which is not energy efficient. Therefore, a trade-off between clipping distortion and energy efficiency should be made. In order to avoid DC bias to achieve higher energy efficiency, ACO-OFDM is proposed, which leaves the even subcarriers unmodulated to obtain an anti-symmetric waveform. For each positive time domain signal, there is a negative signal with the same absolute value at certain position. Specifically, the time domain signals of ACO-OFDM after the IFFT satisfy, whose negative part can be directly clipped at 0, asymmetrically clipped, without information loss. Therefore, the transmitted signal of ACO-OFDM is written as for n equals 0, 1, n-1, where ICO niche the negative clipping distortion of ACO-OFDM. Interestingly, the FFT of ICO, denoted as ICO, only falls on the even subcarriers, which does not interfere with the useful information. Therefore, a simple FFT can be used at the receiver for detection. PAM-DMT is also an asymmetrically clipped method to generate non-negative OFDM signals. Unlike ACO-OFDM, the imaginary part of all subcarriers is utilized for data transmission, while the real part is left unused to produce an anti-symmetric waveform. For the imaginary part of each subcarrier, PAM constellations are employed. The time domain signals of PAM-DMT after the IFFT satisfy, and the transmitted signal of PAM-DMT denoted as SPAM, NC can be obtained similar to 4, while we denote the negative clipping distortion of PAM-DMT as a PAM, N. The FFT of a PAM, represented by a PAM, only falls on the real part of each subcarrier, which does not interfere with the useful information similar to ACO-OFDM. Therefore, a simple FFT can be employed for detection at the receiver. In U-OFDM, the signal N, 2, is utilized to generate non-negative signal. Unlike DCO-OFDM where the DC bias is used to make the signal unipolar, the OFDM frame is separated into two frames with the same length. In the first frame, all the positive signals remain the same, while the negative signals are clipped at 0. In the second frame, all the negative signals are replaced by their absolute values, while the positive signals are set to 0. At the receiver, the second frame is subtracted from the first frame to recover the original signal. Afterward, the FFT can be used to the resultant signal for detection similar to DCO-OFDM. It is noted that, although ACO-OFDM, PAM-DMT, and U-OFDM do not require DC bias, only half of the resources, in either frequency domain or time domain, are employed compared with DCO-OFDM. Therefore, their performances are better than DCO-OFDM only when low-order constellations are used. When high spectral efficiency is required, DCO-OFDM is more preferred since all the resources are used. Recently, some hybrid optical OFDM schemes have been proposed to achieve better trade-off between spectral efficiency and energy efficiency. In ADO-OFDM, the ACO-OFDM signal is superposed by the DCO-OFDM signal, where only the even subcarriers are modulated by DCO-OFDM to avoid the interference. In this way, all the subcarriers are utilized for modulation, leading to improved spectral efficiency. At the receiver, the symbols on the odd subcarriers for ACO-OFDM are firstly demodulated after the FFT. In order to detect the symbols on the even subcarriers for DCO-OFDM, the clipping distortion of ACO-OFDM should be eliminated firstly, which is estimated by the recovered symbols of ACO-OFDM. However, DC bias is still required in ADO-OFDM, although the power is reduced, which is inefficient in terms of power. In HACO-OFDM, ACO-OFDM is combined with PAM-DMT whose even subcarriers are modulated by PAM. The odd subcarriers in PAM-DMT are also left unused as in ADO-OFDM. Therefore, it is very similar to ADO-OFDM at both the transmitter and the receiver. Since PAM-DMT does not require DC bias, HACO-OFDM is more energy efficient compared with ADO-OFDM. However, the real part of even subcarriers is unmodulated, thus its spectral efficiency is still limited. To fully utilize the frequency resources, LACO-OFDM is proposed in REF, where multiple layers of ACO-OFDM are combined for simultaneous transmission. Different layers employ different subcarriers to generate the non-negative ACO-OFDM signals, while successive interference cancellation is used at the receiver to recover all the symbols in each layer. Compared with conventional ACO-OFDM, the spectral efficiency of LACO-OFDM is approximately doubled with the same constellation order. A similar method is applied to U-OFDM called eU-OFDM, which combines different depths of U-OFDM to further improve the spectral efficiency. In different depths, various repetitions are required so that they can be recovered at the receiver.